Okay, so welcome back. This is chapter 17, section 1. This is part 2. So we left off right up there talking about octants and all that. Now we're down here where we're going to take a look at graphing something in 3D. In this case, we're going to take a look at graphing a plane in 3D. Now, if you think back to geometry, plane was a flat, three-dimensional surface like the floor or the ceiling or a wall. A sheet of paper is a plane, as long as you don't curl it or bend it if it's flat, a plane. All right, so in three-dimensional space, the graph of the equation of ax plus by plus cz is equal to d is a plane if, there's a typo right there, isn't there? That should say is. A plane if a, b, and c and d are all not 0. So some of them can be 0, but not all of them are 0. You get a plane. All right, so what does that mean? Well, if you take a look at that equation a little deeper, so let's zoom in on it. If we take a look a little deeper, what you'll notice is that the variables in this, so let me get rid of that highlighting. The variables in this, the x, the y, the independent variables, the z, the dependent variable, are all linear. That means that there are no exponents on any of them. They're not raised to the second or third or something like that. They're not rooted. They're just plain old x, plain old y, plain old z. This a, this b, this c, and that d are just constants, like a 3 or a -5 or something like that. And so basically what it is it's the three-dimensional analogous to the ax plus by equals c, which would be a line in 2 dimensions. And if you take a line and take it into 3 dimensions, that's simple shape. And I use the word simple a lot in math, but simple doesn't mean easy. In mathematics, simple means uncomplicated. And so this is uncomplicated because the variables have exponents of 1. We're not talking about raising things to powers or rooting or anything weird like that. There's no logarithms or anything like that. So that's what a plane is in 3D. So let's take a look at what one would look like. So we're supposed to sketch the graph of this plane right here in that first octant. So that means in the part of the plane where the x's, the y's, and the z's are all positive. Okay, so what we're going to do here is we're going to use a technique where what we're going to do is we're going to set one variable equal to 0, and then we'll set a second variable equal to 0, and we're going to find where that plane will intersect each of those axes. So this is kind of similar to back in your college algebra, where if you were trying to find the equation of a line, let's say the line looked like that, you'd want to find this and this, because if you knew those 2 points, then you knew what the line looked like and you could sketch it in. So you'd find the y-intercept and the x-intercept, and you'd find the y-intercept because the y-intercept over here was when x was 0. And then you'd find the x-intercept, and the x-intercept over here was when y is 0. Well, we're pretty much going to do the same thing, but we're going to do it in 3 dimensions. So if I want to find the x-intercept, if I want to find the x-intercept on this axis, well, that needs to be when y is 0 and also when z is 0. And if I want to find the y-intercept on this axis, that's going to be where x is 0 and also where z is 0. And then the z-axis, I'm sure you figure out the pattern here, that will be when x is 0 and also when y is 0. So we're going to find that x-intercept. So we're going to make y be 0, we're going to make z be 0, and we're going to put that into that equation, and then that equation becomes 2x equals 8, so x equals 4. So I know that it's going to cross the x-axis over here at 4. Now I'll do the same thing, the same logic, and I'll find where it crosses the y-axis. So that will be when x is 0 and when z is 0, and then putting those in, I get then the equation 2y equals 8, which means that y equals 4. So it's going to cross right here at 4. Now if this was 2 dimensions, I would just say, okay, draw a line that connects those two. But it's 3 dimensions, so it's not just a line. Okay. Now I need to find that z-intercept, or where it's going to cross that z-axis, and so that's going to be when x is 0 and when y is 0. And putting those in, I just get the equation z equals 8. Now, if you're wondering where this, and this are coming from, I'm using this equation up here. I'm using the formula, if you will, for this plane and just replacing the variables with the values. So when y is 0 and z is 0, those two terms go away, and I just get that 2x is equal to 8. Right? All right, so back to this. I get that z is just plain old 8, so z is way up here at 8. And so my three-dimensional piece of the plane that's in the first octant, sorry about that, the landscapers are doing their thing, goes from there to there, there to there, and there to there. And it's this surface on here. It's almost like a triangle when you look at it. And that would be the graph of that plane in the first octant. Now, this is highly unrealistic in the sense that it's very, very challenging to graph three-dimensional objects on a two-dimensional surface. So realistically, what you would do is you would use something like this. This is a website called Geogebra, and it does 3D calculations. And so if I were to type in my equation, it was 2x plus 2y plus z equals 8, I would get this plane. Now, one of the goofy things about this is it doesn't use a standard orientation for the picture to begin with. If you look over there on the right, and I'm sorry, but I can't highlight on the screen, the z-axis is the blue one going up and down. The x-axis is the x-axis is the red one, and the green axis is the y-axis. And so we'd have to rotate this graph around to get it to look like what we want it to look like. And now it looks more like what we were graphing a moment ago. And you can see the intercepts where it's crossing the red there at 4, the green over there at 4, and the graph doesn't quite go high enough on that z-axis to see where it intercepts up there, but we could make that a little smaller, I think, and maybe see it. I don't know. I haven't played with this too much because we don't do a lot of this to see it. I think maybe under settings I could change where my axes were and all that. But that would be what the plane looks like. And this is a much better way to look at it too, because now I can look at it and spin it around and look at it from all different directions versus over here trying to draw this thing. I think that this is good for the tools that I have, but it's not how I would do this. This is how I would do it if it was 1960. Yeah, by hand, that's the only option I got. It's 2022. Let's use some technology and make that work. Okay? All right, so let's just back up a little bit. What's my job here? My job is to graph a plane. A plane is that flat surface in three-dimensional space. This one's tilted at an angle, but it's still a flat surface. How do I know it's a plane? I'm looking at this equation right here, and this equation tells me it's a plane. All three variables are linear. The coefficients are just numbers. That a, the b, the c, and the d are just numbers. Constants, if you will. Right? And that makes it a plane. I'm only asked to graph the part that's in the first octant. That's where all the variables are positive. I find the intercepts on that x, y, z axis. I find an intercept by setting the other values to 0. So I find where it crosses the x-axis by setting y to 0 and z to 0. The y-axis by setting x to 0 and z to 0. And the z-axis by setting the x to 0 and the y to 0. Okay. If I have a more complicated object, or if I want to sketch more of these planes, what I'm realistically going to do is I'm going to use some sort of technology. Right? But I am going to sketch a couple of these by hand because I want to talk about them as we're working through them. So first off, my job is to sketch this plane. And so I want to take a look at what that equation is because I'm seeing something weird here. Did you notice that the y is missing? Right? There's no y variable in that. And so basically I just have x plus 2z is equal to 4, and there's no mention of the y. So what would the graph look like? Okay, so remember, this is our x, this is our y, this is our z, this is positive, this is positive, this is positive. I mean, if I try to find the intercepts, I can still find the x-axis intercept. The x-axis intercept over here is going to be at 4. If I set that z to 0, the z-axis intercept is going to be, let's see, the z-axis intercept is going to be, let's see, if x is 0, then I've got 2. But what's the y-axis intercept? Well, basically what this is saying is, by missing that y variable, y can be anything, but it's never going to intercept. It's never going to intersect that axis. And so basically this is going to be extruded out and become kind of like a sheet like this, and then going on. So it's like a ramp almost that is at an angle so that the y-axis never punches through that thing ever. Now, I can try to draw these things, but they're really hard to draw. Why not just come over here? We'll delete that one. We'll put it in. It was x plus 2z equals 4. There's my plane. Do you see what I mean about how it never intersects the y-axis? It's like a ramp at an angle. Because the y value is missing, it never crosses the y-axis. In fact, if you look straight down the edge of the plane, that edge of that plane is parallel to that y-axis, which is why it never intersects it. Right? Using that exact same logic, do you see how there's no x? So this is going to be a ramp, just like the last one. That's going to be the surface of the ramp is going to be parallel to that x-axis. It's never going to intersect that x-axis. So let's go take a look at it. Let's get rid of this one, delete. And it was y plus 3z equals 9. So now when I bring this up and look at it, do you see how it's now parallel to the red, which we said was the x? If I look down that, it's never going to intersect. And it's kind of that ramp that we were talking about. Okay. Realistically, if you're ever going to graph something in three-dimensional space, this is what you're going to use. You're going to use some sort of tool to graph it for you. Right? Are there other surfaces out there? Sure. Right? We're already at almost 13 minutes, so I'm going to stop this video here. I'll come back and we'll do part 3, starting right here with graphing some surfaces, which is where we're going to start talking about, as the equations get more complicated, the weird shapes that these things take on. All right, I'll see you all back here for part 3.